Hi everyone, thanks for listening this message. In recent times, we got messages that do we have any program, any course where we can go enroll and we will be very much eligible for the job market. What does it mean? That if you go and check the IT portals, you can see that you have different course packages for CCNA, then CCNP, then firewall, then cloud, then automation, etc. Right? So what we have done that we created one program for those engineers who want everything at one place and they are new to the market, or maybe they want to enhance their skill set. So we created such program, Joint. Joint is something like job-oriented internetworking training. Now, in this program, you can see that we have added CCNA routing switching, cloud virtualization part of VMware, CCNA or associate level wireless knowledge, Cisco Meraki, Google Cloud associate level knowledge, not entire course, but how much you need um, to get clear in your interview, or when you are working on this cloud environment, you are not new to that cloud environment. Then Python, then routing switching, ASA firewall, and then we are adding firepower as well. So not only ASA firewall, but next generation firewall. Then we are going to add Cisco SD-WAN, Cisco DNA, etc. Like what we want, that we want to make this course as a complete package course, in terms that once you go and complete these areas, you can write in your profile, in your CV, that you know these technologies. And apart from that, not only this course, once you go and use the Joint 9, that's the code here, and if you apply, you will get maximum 85-86% discount on this course. So not only that we are offering the discount coupon, but apart from that, we are giving the lab, EVNG lab. So whoever will go and join this particular course, they will go and get the EVNG lab as well, so they can practice routing switching, right? So what you need a solid foundation, solid course where you can gain the technology knowledge. Then you need the lab environment where you can go and do hands-on practice. And then you can go and add these areas in your profile and go for interviews and all, right? So on other words, in simple words, I can tell this thing that if you go to Udemy or YouTube, I have so many different courses I created just to obviously earn money. So many courses I have, but this is the only course I created actually for the IT professionals, actually for you, where I want that you can go and get the job. That's why I have added whatever I have 15, 16 years of training experience. I have added all the best things from there, in terms of that you gain knowledge, whatever gray areas you have. Someone knows networking, don't know automation and cloud. Someone knows networking, they don't know firewalling technology, security areas. So that means that you can go enroll this course, gain the knowledge on those areas that you don't know. Or suppose if you have only 1 or 2 years of experience, then you can start this journey, complete the entire course within 5 to 6 months or maybe 3 months, and then add these things within your CV profile and get the job. So this is something like job oriented or career oriented training that is going to help you to get the job and right knowledge to showcase in your profile. All right, thanks for watching this video. In 1.1d, we have to understand about first hop redundancy protocol. Although there are three, HSRP, VRRP, and GLBP. But in this section, we just have to learn that how we can go and apply FHRP. And in the upcoming sections, what I planned that we'll go and learn the theory of HSRP and then the lab, theory of VRRP and then the lab. So next 4 videos, you will understand that what's the usability of FHRP, why we are using FHRP, And then how you can go and use this over various devices, either Cisco router or switches. In 3.4c, we have to learn about FHRP, and we have to understand the theory, and then we have to perform the lab task as well related to first hop redundancy protocol, that is the hot standby redundancy protocol, HSRP, and then VRRP. All right, so let's start with HSRP. Uh, First of all, why we need first hop redundancy protocol? We need first hop redundancy protocol because you can see this diagram here. You'll find that, okay, I can go and reach to the switch and then I can go out, or I can do anything, correct? The problem here is that suppose if this link will go down, then what we can do? Obviously, all the devices in the network, they will lose the control. Why? Because you have only one path, you have only one dependency. So you don't have triangle in a network, or you don't have loop in a network, or you don't have redundancy. Suppose if you have this type of connection, and then if these devices can work as an active or a standby or primary or secondary, if this link is down, still you have the way that you can go and reach outside, correct? So that's actually the concept, or that's actually the need behind creating the first hop redundancy protocol. Now, doing so, there is one other problem. Suppose if you want to use this path via this switch, so what will be the gateway address to the host? Because generally we used to hard code the gateway address. So either gateway address will be this switch physical interface, so this interface here, or maybe this interface here. Suppose if your switch is down, this end host machine, they can't dynamically change the gateway. So rather than, what is the strategy here is that you should use some virtual gateway, or you should have some virtual router in between these physical devices falling in the same network, and that virtual IP we are going to give as a gateway address to the client. So either if first or maybe second switch will go down, there is no impact in a network. So we have the label of redundancy. Now we have multiple protocols. We are going to discuss about hot standby redundancy protocol. Here you can see that you have switch 1 and switch 2. One is working as a active, one is working as a standby. Rest other devices are the listening router. As per the highest priority, so there is priority. So for example, 200 versus 10, so higher is better. As per the highest priority, one of the device will work as a active, and then rest of them will work as a standby and listening. In a group, we can go and put say 16 devices. So here you can see that you have priority from 0 to 255, and default is 100. Higher is better. So what does it mean? It means that although you have the virtual IP, and suppose his priority is 200 and this priority is, although it is written 100 and 150, but let it be, this is 100. So the traffic will go in this direction. Now what will be the fallback? If you have LAN interface will go down, obviously they will do some sort of re-election, and this device, because one is unavailable, so you have one other path that you can go in this direction. But again, there is one question that what will happen if your WAN interface will go down? Okay, so there may be chance that your switch will go and reboot, your this interface will go down, your WAN interface will go down. What will happen with the active traffic? What will happen with the flow of the traffic? How it will converge? How there will be the fault tolerance, etc. Okay, so we can discuss that. Never mind, one by one. First of all, when we have the two routers in a group or two switch in a group, we can go and create, or we can do the HSRP configuration. Then they will go and elect who is the active and who is the standby. And the message that they are going to send across in between devices are, say, initial, learn, listening, speak, standby, and active. So in active state, we have this devices that is actively, means they will form the HSRP neighbor relationship. We can't tell that neighbor relationship, but they will form the HSRP in between them, and one will be the HSRP active, one will be the standby. So here you can see that in the active state, an interface in an active state is the live gateway and will forward traffic sent to the virtual IP addresses. Host will use the virtual IP as their gateway. The active router will respond to the ARP request for the virtual IP and the virtual MAC. So far we have discussed about virtual IP, but we have one other concept as well, that's the virtual MAC. Now the hello packet exchange for HSRP, we have is speak, standby, and active. Okay. All right. So let's quickly discuss about the virtual MAC. And once you go and do the basic configuration, I'll show you that virtual MAC in the next slide. So you can go to the interface, or you can go to the interface VLAN. You can go and use this command standby. You can define the priority. You can go and define the virtual IP, etc., etc. We'll see all these things in the lab. Then here you can see that this is the diagram, although our lab diagram is a bit different. I'll show you in the lab diagram. So these things I'm going to configure in the lab. Instead of interface VLAN, I'm going to use any Ethernet interface or any physical interface. So you can go and do the configuration. Now, important thing here, you can see that the ARP response will come from the virtual MAC. So this particular virtual MAC, what is the format? So here you can see this is the format 000.0C07AC, and then the group number. This XX is in the hex that will represent the group number. So suppose if I go and give the HSRP group as 10, if you convert 10 into the hex, it will come 08. So that's why the final MAC address is 000.0C07AC08. Okay. We have this. If you want, we can do the MAC address manual configuration as well. If you want, we can do the authentication configuration as well. Then we have the concept of prompt. So what is mean by print? Suppose this is active and this is a standby, and it will go and reboot. So this will become active, but suppose if will come back online. So if you enable the prompt feature, that means when the active will come, the system will detect, oh, he has the highest priority. So for example, he has a priority 200, he has a priority 100. So this guy has the highest priority. That means again he will become active and he will become the standby if we do the prompt, if we enable the preemption. Otherwise, active will be active, a standby will be a standby. After the failure, standby become active, he will be the active. Okay. So we have the command. We can go and use a standby one prompt. If you want, you can disable the prompt as well. Apart from that, we know that we have the timers for HSRP. By default, that will be 3 second and 10 second. 3 second of hello timer, 10 second of dead, means you are sending 3 packets. Fourth packet, you are not getting response. You'll make that your HSRP group partner is not active, maybe some issue, maybe you have a split brain issue, etc. They're using the multicast address 224002 and the UDP port 1984 for this particular hello exchange. If we want, we can give the time in milliseconds as well. So if you want aggressive timer, if you want fast convergence, you can go and change the hello timer. We have a few of the verification command that we can go and check show a standby. We can go and check show a standby brief. All right, so we have few more slides related to failure as well. So let's complete these slides, and in next session anyways we have to do the lab, so I'll go and discuss more and more in that. Now here you can see that tracking. Say for example, this link is down. Suppose his priority is 150 and this guy priority is 130. So obviously he is active and he is a standby. Now what you can do, you can track the interface that is going to WAN, say 223, and then you can decrement the priority, for example, 60. So if you decrement the priority, if this link is down, what will happen? This priority will become 90, and this is what 130, 130. So that means the traffic will go in this direction. And that's the use of the live tracking, or that's the use of the tracking, that you can track the interface, you can decrement the priority, and the standby will become the active, and the traffic will go in that direction. All right, so these are the points you have. At this point of time, you can think that how we can check this link. Obviously, this link is tracked. If this link is down, automatically it will go in this direction. If this device will go, obviously it will go in this direction. If this is down, you should do the track and then decrement some sort of priority. So this direction will go in, and this traffic will go in this direction. All right, so these are the concepts related to HSRP. Let's stop here and perform the lab task. All right, so in this section, we'll go and do the configuration related to HSRP. Now for HSRP, we'll go and make a spine 1 and a spine 2 as this HSRP gateways, where a spine 1 will work as a primary, spine 2 will work as a secondary, because we'll make the spine 2. Within a spine 2, we'll make priority as a 50. We know that by default priority is 100. So the higher priority will be the active and the lower will be the backup or a standby. So what we want to do here, what configuration we want to do here is that let's go and go to spine 1. First of all, we need to enable the features, right? So already we have enabled the feature called interface VLAN in the previous section, maybe in the section where we are doing the configuration related to VLANs, the spanning tree, and the port channel, right? So anyways, if you want to assign the IP address over the interfaces, you have to go and enable the feature called interface VLAN, and then we can go to the VLAN. So for example, VLAN 10, already we have created this VLAN. If it is not created, we can use the VLAN 10, 20, those commands to create it. And then the IP address will go and assign 10.10.10.1/24. And then interface VLAN 20, the IP address 20.20.20.1/24, right? Then we should go and enable the feature for HSRP. We know for everything we have to enable the feature within the switch. And then within the interface VLAN 10, I can go and give the IP. So we can go and give the HSRP. You can see HSRP, and then we have multiple options like use burnt in address, versions, MAC, refresh, delay, group number, HSIP 10, IPv4, and then IP. The gateway IP that you need to give. These things will already covered in the theory section. And then the permission. Likewise, we'll go to interface VLAN 20. Here also we can go to the HSRP. And here also we can go to the group IP, or you can press enter as well. It's up to us that we are giving HSRP 20 IPv4, etc. And then IP 20.20.20.254. That's the VIP IP, and here also we want to do the print. Right, and then sure an HSRP. Let's see that HSRP configuration. So here we are. You can see HSRP, VLAN 10, HSRP, that's the group number, print, and then the VIP IP. Likewise, we can go to the spine number 2. Here also, we should go and enable the feature for interface VLAN, which is already there, but we should go and create it. Feature enable feature HSRP. Then we can go to interface VLAN 10. IP address 10.10.10 dot here it is 2, and then interface will should be 10, right? No problem. 20, no IP address, and interface VLAN 10. You should give this IP over 10, and then we can go to interface VLAN 20, IP address 20.20.2/24, no shut, and then we can go to the HSRP, right? So now I'm inside interface VLAN 10, where I want this HSRP group ID 10, VIP IP will be the same, 10.254. Here also I can enable the permission, but the priority. So priority here, I will go and give lesser priority. And then I can go to interface VLAN 20. This is HSRP group 20. The VIP IP is 20.20.20.254. Also permission enable. And here also I'll go and give the priority as less as 50. So now once we have done this configuration, the same way you can do the configuration for VRRP as well. So that's why I'm not configuring VRRP, because both are almost the same type of configuration. So now we can go and check show HSRP brief, and we can see that for VLAN 10 it is it's the group address. So VLAN 10, what's the group address? 254. Priority is right. Strange. Sure, an HSRP. So here you can see the gateway IP 10.10.10 and sure an interface VLAN 10. Interface VLAN 10. Let's quickly check these configuration, right? And 20. So 20 group is 20, permission is correct. 10, no shut. So interface VLAN 20, no shutdown. Show HSRP brief. And let's go here. Spine number 2. Interface VLAN 20, no shutdown. Interface VLAN, obviously 10 is working fine. Show HSRP brief. Show an interface VLAN 20, no shutdown, primed priority, and 10, no shutdown, primed priority, and now you can see this is active, this is local, and the standby IP. You can see this is the standby IP, and here also you can see that priority is 50, so that's why it is working as a standby. So this way we can go and do the configuration related to HSRP. And one more thing, that if you see the diagram, we don't have anything connected with 1.6, and I have assigned some IP here, 1.6. So I'll do no IP address. Okay, this interface is up, no problem, but we don't have IP on this interface. All right, so let's just stop here. Next, we have VRRP. VRRP is nothing but virtual router redundancy protocol, very much similar to the Cisco HSRP. The difference is that this is the industry standard and HSRP is Cisco standard. Almost they are same, but there are a few differences. We'll see that what differences they have. First of all, you can see their timer is 1 second. Then you can see that the MAC address is 224.00.18. The VRP print is Print is on by default. VRRP cannot directly track interfaces. It can track an object which is tied to an interface. Okay, so you can see that there are some difference, and again we are in the existing WAN. If you go to SD-WAN, specifically Cisco Viptela SD-WAN, in that we don't have HSRP, but we can run VRRP, and there we have the customized VRRP that I have explained in my SD-WAN course that you can refer. So VRRP in the existing WAN, VRRP in the SD-WAN, both are very different. Now this VRRP is very much like HSRP. It is working as a gateway, so we can have the virtual IP, we can have the priority. Again, higher priority is better. We can go and tune the timers. We can have the we can go and enable the authentication. We have the reserve MAC address, which is different. There we have the different MAC address. Here you have 4 times 05 E00 dot 01XX. Okay, and here the name of the primary, say active, and the standby is master, and the backup that will go and verify uh, in the lab section. We can go and use no VRRP print, because by default this will be on. You can go, if you want, you can disable. You can go and check show VRRP. Very much same type of output you'll get that you have in HSRP. Now we have one very interesting topic here, that do VRRP and HSRP can do the load balancing. Because for load balancing we have Cisco proprietary protocol, that is GLBP, that is not in this particular course, but we have discussed earlier in section maybe 1 or section 2 that how this GLBP is working. uh, GLBP is not that popular like VRRP or HSRP, due to some GLBP. They have some reason behind that. They have some internal reason. The active forwarder or the standby, they are not able to do a load balancing in failure scenario, etc. Means they have some internal issues with GLBP. You will find that most of the places we are using either HSRP or VRRP. Now suppose you want to do the load balancing. You know that one of the router is active, one is a standby, and suppose if you have thousands of client or endpoint, you want that 500 will go via one router and 500 will go via other 100, the 500 will go via other router, then how we can achieve that? So what I'm telling here, let me try to draw, and even you can see the configuration. That's the manual load balancing configuration we have. So what I'm telling here, that say I have these two devices, and they are part of, say for example, VRRP or maybe HSRP. Now we know that one is active and one is standby, or one is master and then backup in case of HSRP and VRRP. And suppose if you have 1,000 users or 1,000 clients, then obviously as per the standard configuration, 1,000 of the devices will go via one gateway, one active gateway. So there is no load balancing. Rather, what we can do, that we can create group. So here you can see that inside VLAN we are creating one group, and then we are creating other group. So one group is having higher priority, other group having lower priority. Obviously the VIP is different, virtual IP is different. Likewise, that means that as a whole, this will be the active for 500 user, and this will be the active for 500 users, and as a whole they will work as an active load balancer. Okay, now once you have this configuration and you want to check it, verify it, you can go and check show standby brief. So in that output, what you will find, that you will go and get the output related to both the groups. So here you can see that you can see the first and the second device, active standby, standby active. Now this is not the limitation, but actually this is the feature, that we can do the manual load balancing across the routers. All right, so let's stop here. We'll do the VRRP lab that we have done like HSRP, and then we'll check this load balancing methodology as well. We have completed 1.1 section. Now we are in section 1.2, where first of all, we have to learn, understand about RSTP, LACP, and VPC, virtual port channel. Now what I have done that again, here we have to learn about how we can go and implement these protocols. But what I have done here is that I created videos related to theory as well. So it will go and start with EtherChannel and primarily focused with LACP. So that theory and the lab. So two videos are related to that. Next two videos, you will learn about RSTP, Rapid Spanning Tree Protocol, and its lab. So total four videos you will watch related to section 1.2 RSTP plus LACP. And then in the upcoming section, I will go and start VPC because VPC, virtual port channel, is a big topic. So again, I will create some 5-6 videos related to VPC as well. So please go and watch coming 4 videos related to LACP2 and RSTP2. And then we'll go and start our VPC topic. We know that Ether channel is something that we can bundle the interfaces to overall increase the throughput. So here you can see in the diagram that you have core, distribution, and access layer. Generally, where we want to do this bundling or aggregation of the port or interfaces, they are at the level of core and the distribution layer. Generally, that doesn't mean that we can't do at the access layer. We can do as per requirement. So what we are achieving with Ether channel or the port bundling, that we want to give much more throughput whatever we have at this point of time when you are connecting the interfaces back to back. That simply means very simple term that suppose I have switch A and switch B. So let me try to draw here. Say for example, one switch here and one switch here. If I have 1 gig interface, then obviously the overall throughput is 1 gig. But you can take, say for example, 4 interfaces and you can bundle and they can work as a 4 gig interface. So overall throughput obviously will increase, will become 4 gig. Now the important thing here is to understand is that this 4 gig interface is per application. Means suppose if you have only one application and you think that one application is getting 4 gig of interface, that's not true. The algorithm or mechanism behind the scene is that suppose if you have two interfaces, they will do the load balancing. So 1 gig and 1 gig will get load balancing or get load balanced per application flow. That's the key thing we have here. Whenever we are doing the port bundling, that doesn't mean that this become one 4 gig pipe and all the applications are getting 4 gig of speed. It's not the same thing. All right, so we have different type of methodology behind this, and we'll see that we have LACP, Link Aggregation Control Protocol, and we have Cisco proprietary, that is the PAGP, Port Aggregation Protocol. But moral of the story is same, that you are aggregating the port for higher throughput. Now we have to go and check that how we can create this Ether channel or bundle. We have option, we can do it manually, we can do it dynamically as well. Manually when we are talking, so for example, I have two interfaces, I can go and I can use this command interface range and then channel group 1 mode on, or maybe you can use some other number like 10, 20, 30, 40, etc. So when you are using mode and on, and we have multiple option. So for example, in LACP we have option related to active, passive, and on. So for example, if you are using on, this is a manual thing. Manually you are turning on this LACP protocol or channel protocol. Okay, now once we are running this command, what is happening behind the scene, automatically port channel interface 1 will get created. Now this port channel 1 interface that you are creating, here you have to go and write your logical configuration, or you have to do the coding. So for example, if I have two interface 23 and 24 and I want to run commands related to switch port mode trunk and allow certain VLAN, then I do not have to run the command over the member interfaces. Rather, I have to do it inside the logical interface. So we should understand some of the technical term here, that I have a switch and I have two member interfaces. So for example, 23 and 24. When you bundle these interfaces and you are using manual method turning, so for example, LACP on, so at that point of time, so for example, the group you are using is 1. So you are going to create interface port channel. Here you can see this port channel 1, and whatever configuration you want to put over these interfaces, you should put here over the port channel. The switch port mode trunk and allowed VLAN we should put there. Suppose if you want to create a layer 3 port channel, then you can go to the port channel, you can do no switch port, and then you can assign the IP address as well. Okay, so this is the manual way to do the configuration, although we have the automatic way as well, and we have the protocol as well to do this. We'll see that in the upcoming slide. One important note here, that whenever we are creating the port channel among 2 or 3 or 4 switches, obviously these are point-to-point configurations. So in between two switch, whenever you are creating the port channel, so at that time your speed, duplex, and other hardware related properties should be the same. So what I am telling here, that you are creating port channel here, no problem, you can create it like that. You can create other port channel here, so for example number 10 and 20, etc. So these interfaces, so for example speed, duplex, should be same, correct? Otherwise they will not form the port channel, and constantly they will throw an error as well. Alright, so next we have the dynamic way to do the configuration. We have a link aggregation protocol, we have port aggregation protocol. uh, Now everyone is using LACP, and even in the syllabus also it is recommended that we should learn, understand LACP. Although if we learn one methodology, the second will come automatically. So I'm going to focus on LACP, link aggregation protocol. This is the dynamic way to create the bundles. We have mode for LACP is active and passive. If both side of switch is active, they will form the port channel. Both side is, say one side is active, other side is passive, again they will form the port channel. If both side is passive, then they will not form the port channel, because no one is sending the LACP control packets. So obviously both are the listener for LACP, and they will not auto negotiate the ether channel or the bundle. So here you can see that when you are doing the LACP negotiation, means when you are doing this automatically, so you can go to the interface channel protocol, you can define, then you have to go and give the channel group name, mode active. So suppose one side I am using active, other side I am using passive, so they will go and form the port channel. It's very easy and straightforward. There is no much thing behind this. Now we have some important thing related to LACP, that we can have 8 interfaces inside group, and 8 interfaces we can work as a backup. So 8 plus 8, they are supporting total 16 interfaces that can form LACP, but these 8 interfaces are working as a backup. Now who will work as an active? That depends upon port priority. By default that will be 32768, and lower is the better. Okay, now apart from that we have other variable as well. Other variable is system priority. So suppose if you have two switch, and which switch will take the active role and which will work as a standby or secondary role. So who is the primary, who is the secondary? So that depends upon the system priority. By default, that is also 32768, and lower system priority is better. So suppose this is 500 and this is 32768. So obviously he is the active initiator and he has to take the decision. So by default, both will be the same, so that again, if you have the tiebreaker, so in that case, always the lowest MAC address will be preferred. So whoever switch having the lowest MAC address, he will take the decision, because by default, we are not changing the port priority, we are not changing the system priority. So as per the MAC address in terms of system priority, lowest MAC address will win. In terms of port priority, lowest port number will win in case of tiebreaker. Now once you do the configuration, you can go and check show ether channel summary. That's the nice command. There you have the legends or flags. So for example, D for down, P that they are in the port channel, I for a standalone, S for suspended, R for L3, S for layer 2, etc. So you have the legends and you can check the status. So these devices, S stand for layer 2 and U stand for port channel in use. So this port channel is successfully formed. This is layer 2 and up and running. Okay. On Cisco Nexus switch, the syntax is a little bit different, obviously, in the Catalyst switch and the Nexus switch, but the concept behind the scene is the same. So this way we can go and create the port channel. Here you have some difference, means what is the difference between port aggregation protocol and link aggregation protocol. In port aggregation protocol, we are using the mode as auto and desirable. Desirable is equivalent to active, and I think there is some typo here. So desirable is equivalent to active. Okay. All right, so it's not a typo mistake, but in the diagram, there are different use cases. So manually you can do on, either it's a PAGP or link aggregation protocol, they will work. Now on off, one side on, other side off will not form the channel. That's true. Then one side auto, other side desirable, they will form the port channel. Now here you can see that you have auto. So let me write here auto, and then you have desirable. This auto is passive for LACP. So for example, PAGP, and this desirable is active. So if both side is desirable, they will form the port channel. Both side is auto, they will not form the port channel, and same is the case with LACP that we have discussed earlier. So these are the use cases, these are the scenarios we have that will work here to form the ether channel. All right, so what we will do in this lab, that I will go and configure various layer 2 parameters such as spanning tree priority. So what we'll do, you can see the diagram here. Priority. In the diagram, you can see spine 1 and spine 2. So what we'll do, that I'll go and create the VLANs as well. So before that, I'll go and create VLAN 10 and VLAN 20. And for VLAN 10 and 20, a spine 1 will be the primary or root, and a spine 2 will be the backup. Like that, we'll do the configuration. So we'll do the VLAN configuration. Then we'll go and set the STP priority, and then we'll go and create the ether channel. So as you can see in the diagram, that we have ether channel, port channel 200 within this spine. So here you can see within the spine we have 200, and then 100 within the leaf. We can see the VLAN 10 and 20. Apart from that, spine having the uplink going towards the router. Another spine also having uplink going towards the router. In between spine 1 and 2, you can see that we have the port channel, and then we have the downlink where we'll go and make this downlink 1.3 and 1.4 as a trunk port, as a trunk interface. This will make this trunk and will allow VLAN 10 and VLAN 20 over that, right? So why not, let's go here and do the configuration, basic configuration to the Nexus switches in these leaf and in these spines. So let's start with the spine. And once we are here, let me go and do the configuration. All right, so let's log into the spine 1 and spine 2. Close this core. And let me quickly log into this and log into. All right, so in spine 1, obviously we have to go and enable some features. So for example, feature LACP, feature interface VLAN, like that. And in upcoming section, again, we'll go and enable some other features as well. Let's go and do the configuration related to VLAN. So I can go here and create VLAN 10 and 20. And then we know that we have the spanning tree. For that, VLAN and 10 and 20, we want to set the priority as lower. Lower means better, it will become the root bridge. And then we can go to the management. We have the management VRF where we want to set the IP route to the gateway. These are the basic configuration that we want to do here, right? And likewise, we'll go and do the configuration related to port channel. So let's go to the interface E1/1 and 2. And these are the interfaces where we want to enable the trunk. So first of all, switch port mode trunk, then switch port trunk allow VLAN. And these are the short form. Let me write it in the full form. So this command is switch port trunk allowed VLAN 10 and 20, right? And then channel group 200 mode active. Okay, then I can go to interface 1/3 and 1/4. So I can go to 1/3 and 1/4. Why? Because these are the interfaces that is going towards the leaf switch. Here I can make switch port mode trunk. And here I want to allow the VLANs 10 and 20. So very easy, straightforward configuration, right? Then we have one interface that is connected to the router. So I can go to that interface where we'll make no switch port because this is L3 interface where we have IP address as per our IP schema. We'll go and assign the IP address. So one side is 10.10.40.2/24. Other side will be .1, right? Then we'll go to 1/6. No switch port, no shutdown. And then we can go and assign the IP address here as well. We will check that blueprint, what IP we have here over this interface. And according to that, we'll go and assign the IP. Let me quickly go to the spine number 2. And let's do the same sort of configuration, enable the feature, LACP, almost same. Only thing is there, you will see that IPs and spanning to priority, those things will change. Otherwise, almost same configuration we will do here as well. So we have VLAN 10, 20 1, 10, and 20. I have written 20 and 10, but it is VLAN 1, 10, and 20. Then we'll go to the spanning tree and VLAN 10 and 20, and this time the priority that we'll set is more. So that means it will become the secondary. Once we have the priority, then again we'll go to the management VRF, where we want to give the IP route, and gateway will be the same. So default route pointing towards the gateway, that will be the same gateway. That's fine. And then we can go to the interface ranges that we have. So here you don't have to use the range keyword. Go to interface E1/1 to 2. Automatically it will come to the range. Switch port mode trunk, allowed VLAN 10 and 20. I'm writing it here short because earlier we have done in the full format. So channel group 200 mode active. Right, obviously do no shut, then interface E1/3 to 4, that is the downlink, where we have switch port mode trunk, allow VLAN 10 and 20, right? And then I can go to E1/5, no switch port, where we have to go and give the IP address 10.10.60.224. No shut, and then I need to go and check the IP here over 1/6 IP address 10.10.30.2/24. No shut is there. So here the IP, again we'll go and check the blueprint, the IP address schema, maybe 20.2. So you can see how we can go and give the basic configuration, right? Basic configuration to all these places. Once we have all this basic configuration, you can go and check show port channel summary. And now I can see that SU, the port channel, is up. Protocol is LACP between 1 and 2, which is working fine. So we have to go and do the configuration for leaf as well, right? So for leaf also, we can go and do the same sort of configuration. So let me quickly log into the leaf 1 and leaf 2, and let's do this basic configuration. Okay, leaf 1 and leaf 2. Let's try to log in here. And oops. Let me try to log in leaf 1 and leaf 2. Very same style of configuration we have here as well. So first of all, we'll go here and enable the feature LACP. Then we have feature interface VLAN, and then I will go to VLAN 1, 10, 20, and then we'll go to VRF context, that is the management. We'll give the IP route for the same gateway, that is 0000/0 and 198.184.254, like that, right? Repetition, almost same thing, right? Then we have interface E1/1 to 2, where we want to do that port channel configuration. So switch port mode trunk, allowed VLAN 10 and 20, right? And then channel group, here we have channel group 100 as per the diagram, correct? Then we'll go to interface E1/3. Now this is connected with server. So interface 1/3, we have that switch port mode trunk, but the allowed VLAN here, so switch port trunk allowed VLAN in this interface is VLAN 10, and here we are making spanning tree, port type is edge trunk. So servers, when we have servers, we are using this type of configuration, right? So again, we'll go to interface E1/4, switch port mode trunk, switch port trunk allowed VLAN. Here on this interface, we have VLAN 20, and then we have the edge trunk. So this is the interface that is connecting to the server. What about the uplink? What about the interface that is connecting with the spine? Suppose description is spine 1. Right, again we'll go and check that diagram as well. Switch port mode trunk, and because this is the uplink, so here trunk allowed VLAN is 10 and 20. Like that, we can go to E1/6 and you use some up arrow just to save your time, and switch port mode trunk, and switch port trunk allowed VLAN will be 10 and 20. Right. So like that, even I can go and create a copy of configuration and I can paste here, right? So it will save few of our time. Feature is LACP, and then feature is interface VLAN. Then we can go to the VRRP context management, and I can go and paste that. Then we can go to interface E1/1 to 2. And in this interface 1/1 and 2, what we want to do, same configuration. So once we are here, we want to do switch port mode trunk, switch port mode trunk, switch port trunk, allow VLAN 10 and 20, right? And then this command. Then we'll go to interface E1/3 again. Oops. Interface E1/3, switch port mode trunk, switch port trunk, allow VLAN. On this interface, it is, so you have to go and verify the diagram in the leaf number 2. One side we have 20, and other side we have 10. Is just the reverse. So now we'll go to 1/4. We'll make switch port mode trunk, and allow VLAN will be 10. Likewise, the final piece of configuration will go to interface E1/5 and 6. Since both the interfaces we have same sort of configuration, switch port mode trunk and switch port trunk allow VLAN is 10 and 20. If you want to see the configuration, show an interface E1/1, and then 1/2, 3, 4, 5 and 6, etc., etc. Now, what about the port channel configuration? Since we are creating port channel 100 here, I can go to the port channel. I can make the configuration, switch port mode trunk, right? And switch port trunk, allow VLAN 10 and 20. And spanning tree, port type, network, right? Show an interface port channel 100. You can see the port channel 100 configuration. This should be there in the leaf number 1 and 2. Likewise, quickly go and see here. So the interface port channel 200. You can see that port channel 200, we should have configuration switch port mode trunk, allowed VLAN. So what one more line I want to add here actually, that will be spanning tree, port type, network, and oops, last line, So interface port channel 200, because on the spine we have port channel 200, and then we can go and add this configuration item. Now before stopping this video, let's go and check the port channel summary for the leaf, and you can see that it is up and running. So what we have done, a lot of configuration. We have done the configuration related to the, first of all, we have enabled the feature, then we have done the configuration for VRF routing, that's okay, creating the VLANs, creating the spanning port priority, then we are creating the port channels. Within port channels, we are allowing certain trunks, we are configuring the uplink, downlink. All right, so let's stop here. So let's start with RSTP, that is Rapid Spanning Tree Protocol. Now it's very good that if we know the other spanning tree protocols as well. So for example, it's good if we know STP, PVSTP, PVSTP plus, and then RST, and then RSTP, and then MST. But I'm going to revise those spanning tree protocol, at least the core behind the spanning tree protocol methodology. What exactly happening when we are talking about the switching network or switching architecture? So in that case, to prevent from the loop, we are running actually STP. So suppose if we have three nodes connected like this, like a triangle, suppose switch A, B, and C. Now here you can see that if you build your network like this, obviously uh, you will find the loop. So frame will be looped across this triangle. So uh, now again, you may think that why we are creating network like triangles or looped network. The answer is for redundancy. We are creating such type of network so that can provide us redundancy. So for sake of redundancy, we are creating such type of network. So for example, if one link is down, still you have one backup link, or maybe you have other links as well. So two link is down, still you have one link, etc. So for sake of redundancy in a switched network or in layer 2 network, we are creating loops, or we are at least creating such type of network design. Now the question here, second question may be that, okay, since we are creating the loop, then what is the loop prevention mechanism? And then the LTP is the answer. Spanning tree protocol is loop prevention mechanism. What it is doing, that as per the priority, one of the switch will become root, and then obviously you have second root and non-root. But what is happening, that whatever interfaces that is going towards the root, they are termed as a root port. So you have a root port, and whatever interface you have in front of root port, those are termed as a designated port. So you have DP and then you have RP. Now what about those switches where you have least priority? They are not root, they are not secondary root. So in that case, they will go and check the priority. If priority is same, then they will check who has the lowest MAC address. So one of the interface will treat as a blocking, BLK, say BLK as a blocking, and other will treat it as a designated port. So this is the blocking port, and then you have the designated port. So the summary of this explanation is that since you have such type of arrangement, so one of the interface is working as a blocking port, and suppose if your main interface is down, so still the traffic can go from this direction, because from blocking it will move to listening, then it will move to learning, and then it will move to forwarding. Okay, so it will take some 30 to 50 seconds to converge, and after that period of time, the traffic will go from the blocking, because finally it will become the forwarding port. Okay, now here that's a problem, that we don't want to use STP, rather than we want to use rapid STP. We don't want to wait for this time to converge the network, and that's the solution is to use the rapid STP. So let's see that what are the things we have in the rapid STP. This is under 802.1W or rapid spanning tree protocol. It's similar to STP, but there are dissimilarity as well. There are differences as well. We'll see that what are the differences we have. So BPDUs here also you have bridge protocol data unit. These are the, you can think these are the control type of messages upon which the switches, they are building their STP or they are building their RSTP. Here also they will select one root bridge as per the lowest bridge ID, that will be 32768. We'll see that in the next slide. Then the root and designated ports are elected and functional identical to STP. These are the similarities. What is not similar? We can see that here you have root port, alternate port, designated port, and backup port. In other hand, in STP you have root port, designated port, and blocking port. So let me show you in the diagram. It's always easy to understand with respect to diagram. Here you can see that you have the lowest priority, so priority 100, who will become a root bridge. So this guy, and this is with respect to STP, and this is with respect to RSTP. So this guy is the root. Whatever going towards the root bridge is root port. There you can see these are the root port, and then as per the high uh, priority, one will become block, one will be the designated port. If you have any issue in this direction, then it will move to the forwarding state and packet will flow like this. Correct. On other hand, you can see that in RSTP, he is the root bridge, for example. So these are the root port. We have the designated port, same like STP, but instead of blocking, here you can see that you have alternate port. Correct. And if you have two link, so one link is designated port, other one is the backup for the designated port. So instead of blocking, we have alternate port inside RSTP, and that is one of the reason for faster convergence, but there are other reasons as well. Here you can see that instead of blocking, listening, learning, and forwarding, we have discarding, learning, and forwarding phase. So we are not waiting for that particular amount of time, rather than we are moving to the forwarding state as soon as possible, as quickly as possible. Now, initially, a switchboard starts in a discarding state, obviously, then he has to start his learning. Now, a discarding port will not forward frames or learn MAC addresses, as the name suggests. A discarding port will listen for BPDUs. Alternate and backup port will remain in the discarding state. So you have your alternate and the backup port. They are still listening, but they are not actively participating. So they are listening. Otherwise, if failure will happen, how they will start forwarding the frame. So they are not they are not in the forwarding state, but they are still listening the BPDUs. Now RSTP does not need a listening state. Instead, if a port is elected as a root or designated port, it will transition from discarding to a learning. So here you can see that now if you have root selection, then in that case, the port will move from discarding to the learning state. Now what will happen in this case? A learning port will begin to add MAC address to the CAM table. However, a learning port cannot forward frames still. So here you can see that you have three state. In discarding, you are listening that. In learning, you are start learning the MAC address, but in discarding and in learning, still you are not forwarding the packet until unless you reach to the forwarding mode. Finally, when you reach to the forwarding state, then it will send and listen for BPDU, learn MAC address, and forward the frame. Root and designated port will eventually transition to a forwarding state. Okay, so once you have the selection of the root, selection of the ports like root port, designated port, alternate port, etc., they will move from discarding learning to the forwarding state. Now the main question here, that why RSTP has faster convergence? And now you will see the core difference between STP and RSTP. Why? So BPDUs are generated by every switch and sent out as a hello interval. switches no longer required artificial forward delay timer. Now what is happening in this case, that all the switches, they are generating their own bridge protocol data unit and they are forwarding to their peer switch. Okay. Now what is happening in STP? STP code is 802.1d. Now in STP, BPDUs are generated by the root bridge. Now, if switch receive a BPDU from the root bridge on its root port, it will propagate the BPDU to the downstream or its neighbor. This convergence process is slow and STP relies on forward delay timer to ensure a loop-free environment. So now you can understand that rather in RSTP, switches, they are generating the BPDU and sending to the neighbor. But in STP, that is 802.1d, you have one root port or you have one root bridge election. One switch will become the higher authority and then he will generate the BPDU and all the downstream switches will listen as per their delay timer or as per their timer. So you can see here that the default nature of STP is slow rather compared to RSTP. Now in RSTP, switch will handshake directly with their neighbors, allowing the topology to be quickly sync. This allows port to rapidly transition from discarding to the forwarding state without delay. So you have one-to-one handshake, and then from discarding it will quickly move to the forwarding state where they want to forward the packet. Now again, we have some port type in RSTP. We have edge port, and suppose if you know at this point of time about port fast. Port fast is one of the very popular term that whenever you are connecting the switch with the terminating device, say for example server, so you don't want to send the BPDU. So I don't want to send BPDU or I don't want to send STP control packet to the device that is non-switch, which is not a switch. There is no meaning of that. So that's the reason this particular interface, we are making this interface as a port fast, means quickly it will go to the forwarding state. Likewise the edge. Now this edge port is working as a port fast, immediately it is going to the forwarding state. So there is no listening, learning, forwarding like STP, or there is no discarding, learning and forwarding like RSTP, but directly it will move to the forwarding state. Now second port type, we have the root. Root ports are connected with other switch and has the best path cost to the root bridge. Obviously we know that root port is there. That is one side you have root port, other side you have designated port, so you can reach quickly to the root bridge. And then finally you have point to point port. What this point to point port is doing, that port that connect to other switch with the potential to become the designated port for a segment. So it can become DP. And now if you go and refer the actual diagram that we have here, so you will understand. So you have root port that is going towards the root bridge, and here you can see the adjacent to root port is the designated port. Designated port adjacent is root port, but here you can see that you have designated port and backup port as well. All right, finally we have some important notes here related to RSTP. So let me quickly cover this. Now if edge port receive a BPDU, it will lose its edge port and status and transition normal through the RSTP process. On Cisco switch, any port configured with port fast become the edge port. We know that. Say edge port, I already explained this, is port fast. Quickly move to the forwarding state. That's the summary for the edge port. Now the RSTP converge process is below. So let's quickly understand the convergence process of RSTP, why they are converging so fast, and we have discussed this in the earlier slide as well. So let me quickly revise this. Now switches exchange bridge protocol data unit to elect the root bridge. This is valid for all the spanning tree protocol. Now edge port immediately transition to forward state because they are nothing but the port fast. All potential root and point-to-point ports are the or start with the discarding state. So this is actually important. By default, the ports will start with a discarding state. Correct? Means they are actively listening the BPDU. They are not learning the MAC addresses. They are not forwarding the frame. They are learning. So you can think behind the scene. Uh, it's not learning actually. They are listening. So you can think this as a listening active listener. Then if a port receive a superior BPDU, it become to a root port and transition immediately to the forwarding state. So obviously once you learn the BPDUs, then you will move to the forwarding state. Superior means that suppose if you are getting one BPDU, because in this case what is happening, all the switches, they are generating their own BPDs and they are exchanging it. So suppose this switch has low priority, say 32768 the default priority. Suppose this has priority 32769. He has 68. 69 is not a valid number, just for example. So obviously when he receive the PPTU, he will understand, oh, I am getting this with the higher or the superior switch, and then this will become, so this particular point-to-point interface will become the forwarding state. Okay, for point-to-point port, each switch will exchange a handshake proposal to determine which port become the designated. Obviously, you can do the handshake and you have to define who is the designated. It's okay. Once the switch agrees, the designated port move immediately into the forwarding state. So here you can see the convergence is like little bit different than STP. So ports, they are starting with the discarding state and then they are moving to the forwarding state. At the moment you get some superior BPDU, it will become the root port. So again, remember that if he is the root bridge, that means that you are the root port and he is the DP. Okay, so if he is sending the BPDU, it will be superior BPDU. Correct? And when he is sending the BPDU, he is not superior BPDU. So that's why it is telling that it will move to the forwarding state, because you have only one blocking type of a state, that is the discarding. So either you will be at the learning or you will be at the forwarding, and you will be at the discarding, but there are less chances that when you have the superior BPDU, you are in the discarding state. All right, so this is the summary for the RSTP convergence. Now every switch will perform this handshake process with each of the neighbors until all the switch will get sync. Complete convergence happen very quickly within the second. So all the switches, they are sending their BPDUs, and then switches, they are calculating on basis of BPDU and the superior BPDU. Now, whoever is sending the superior BPDU, he has become the root bridge and his interface will become the designated port. The adjacent port will become the root port because he has to reach to the superior bridge, and according to that all the switches will converge. Once they converge, once they sync, then RSTP will up and running to all the switches, and then it will take a few seconds, and that's why it's TCN in STP and RSTP both have different way. TCN is nothing but topology change notification. Now, what is happening in STP, say in case of when the switch move to forwarding state, or in a state of when they are going to blocking or down state, at that time they are generating the TCN, particularly in STP, that is 802.1d. Now that TCN bit will go to the root bridge, because we know that root bridge has to take a decision. Now what root bridge is doing now, that now if they are sending the BPDU, they are setting the TC bit, that is the topology change bit, and then they are forwarding this to all the downstream switches. So all the downstream switch will come to know that the port is going to the forwarding state, or switch interface is going to the forwarding state, or blocking or down state. Correct? Now again, this is little bit time consuming process, rather than in RSTP. What is happening, first of all, only non-edge port when they are moving to forwarding state. So we know that this edge port are working as a port fast, or they are equivalent to port fast. Directly or quickly they are going to the forwarding state. So only non-edge port, when they are transitioning to forwarding state, they are generating the TCN. Now good thing about RSTP that all the switches that they can generate the BPDU and send the BPDU. So in this case, what is happened that they are not waiting for the root bridge to understand or recognize that particular change or that particular topology change notification, and then it will send to all the downstream switch. Rather than the switch, whenever he got that change notification, he will update the other switch. So that's the reason this process is faster. So here you can see that any switch can generate the TC BPDU, allowing the topology to quickly converge via the handsets. Now, a switch receiving a BPDU will flush all MAC addresses learned on designated port except the port where they are receiving the TC or topology change BPDU. So again, the core thing behind the scene is that all the switches in RSTP, they can generate and send the BPDU, and they can sync the RSTP database, or they can sync the RSTP estates. Correct, rather than they will wait for some max edge timer to be expire, or some edge timer to expire, or rather than they are waiting for some central authority, say for example the root bridge, to send the updates, to send the updated BPDU to all the downstream switch in the STP. All right, so here again you can see that we have some flavor of RSTP, and next section we are going to do the lab related to that. We'll learn on more on that. Now here you can see that not only the RSTP, their convergence is faster, but they are taking care of two failure. So either it's a direct or indirect failure. We know that the optimization of STP, if you read that STP, you'll find that you have certain mechanism that you can optimize the STP, like uplink fast, backbone fast, port fast is also one of the optimization technique. So port fast is already taken care inside the edge, or the nature of STP, or the edge port. Edge port is working as port fast. Then for direct and indirect failure, this is also taken care inside RSTP. So we don't need to optimize because these features are already included. So in case of any direct or indirect failure, the alternate ports or the backup ports, they will not wait. Rather than they will move to the forwarding state. Okay. Now we have two implementation of RSTP. One is rapid per VLAN RSTP, that is the Cisco proprietary. So because we are going to run the RSTP on a Cisco switch, so we will go and use this spanning tree mode rapid PVST. And the other one is the multiple spanning tree that we'll study in the upcoming sections. Okay, so we have our lab setup. Let me quickly show you this lab setup and what we are going to do here. So for example, this is the topology diagram that we have. What I can do in this, that, so for example, I have switch 1 and switch 2 and switch 3. So here I'm going to run the RSTP in between switch number 1, 2 and 3 like this. At the moment, I'll not use all the interfaces, all the switches, but this will solve our purpose if we run the RSTP in between that, and then we'll go and run few of the verification commands. Okay, so let's stop here, and in the upcoming section, we have a lab related to rapid PVST or rapid STP. Now we have the lab section. So what we are going to do here, I'm going to run the RSTP in between switch number 1, 2 and 3. They are actually 101, 102 and 103. So here you can see in the diagram that we have the ports that is connected like this, say 1, 2 and 3. So here we'll run the STP, and then we are going to verify that. Here are the interfaces E00 from switch 1 to 2, and then 1 to 3, and then 2 to 3. I'll figure out in the with help of show CDP neighbor, and then we'll run that. So what I'm going to do, first of all, I'll go and create a VLAN to all the switches. So let me quickly go and create the VLAN. So for example, VLAN 10, because we know that all the VLANs, they have their own STP instance. So I can go to this script, and then I can select all. I can go to conf t and VLAN 10, and then we can exit. All right, so send this script to all the switches. All right, now once we have this, and we can go and check show VLAN. So we have VLAN 10. Now we can go and check show a spanning tree. And for spanning tree, we have a few very important and uh, interesting commands that we used to apply all the time, or we used to run all the time, like show spanning tree detail, show a spanning tree summary. So here I can go and run the show spanning tree summary. Here you can see this summary of all these instances. Here you can see that blocking, listening, learning, forwarding, etc. Now we know that by default we are running STP, so that's why you're getting this result. We haven't enabled rapid PVST. We have to change the mode for that. We'll do that. Then you have the detail command. In detail command, you'll come to know most of the things like the topology change, notifications, the timers for STP, etc., and etc. So here you can see that we are dealing actually with switch number 1, 2, and 3. I don't want to add other switch and the interfaces, but we have so many interfaces that is coming here. So let me try to run few more commands, and then we have, say, interface. This is also very important command. So for example, interface 0/0 and enter. So now with this command, I can see that this particular interface is in forwarding state. The role is designated, and like that, I can go and check. So basically, say for example, I have 3 switch, and in this switch, I want to know that who is my root. So suppose I have switch 1, and then I have, say for example, switch 2 and switch 3. They are connected like this. So let's try to figure out first of all who is the root. Okay, so for that I can go again back to the show spanning tree detail, and here we'll see that who is the root for VLAN 10. I am not considering VLAN 0, so let's leave this VLAN 0. Everywhere we are seeing this VLAN 0. So let me quickly go and check that do I have VLAN 10 everywhere. So I can see I have VLAN 10 here, and then I should have VLAN here. So I have all the VLAN, although I haven't added any interface inside the VLAN 10. So what I will do, that I'll move some interfaces inside VLAN 10. So let's do that. I'll show CDP neighbor. Let's check that who is connected with switch number 2 and switch number 3. So here you can see these are the interfaces. I can go here, interface range E0/0 to 1, and this is switchport access VLAN 10. Likewise, I'll go and select the range that is from, here you can see 0/2 to 3, and this is also I'll make as switchport access VLAN 10. Okay,
I'll go to switch number 2, and here also we'll run SocialDP neighbor conf interface range E. Let's see. So we have 0, 0, 0, 1, 2 until like that it is connected. So from 0, 0 to 0, 3, and finally we go to switch number 3, and we'll check that neighbors for 1 and 2. So these are the ports. So I can go here and do interface range 0/0 till 3, switch port access VLAN 10. All right, because we want to verify this only for VLAN 10. So spanning tree VLAN 10 and then detail. So now here you can see this is telling you the information about VLAN 10. That's okay. And if I go inside VLAN 10 and if I go and check who is the root, so here you can see that the root port ID is this, the priority into the MAC address. So let's verify that this MAC address belongs to which particular switch, correct? So now if you go here and check, your MAC address is AABB C006500. Now if you see this particular output, and what is the priority? 32778. Why this is 778? Because 32768 is the default priority plus the VLAN ID. So that's why it is showing like this. So everywhere you will find that the priority is 32778. So whoever has the lowest MAC address, that switch will become the root, correct? Root bridge. All right, so let's continue this. All right, so we can verify like this, and because we have two interfaces connected, so you are seeing interface E0/0 up to 0/3. Although if you go to any of the port and you'll see the detail, you can see clearly. For example, E0/2 for VLAN 10 is the designated forwarding, that is the DP. Whose cost, whose port priority, port identifier, you can see here, they have the priority of 32768 plus 10, that's the VLAN number, and this is the address. Now the designated bridge has priority this is the MAC address. Then again you can see the port priority and all other data. Now the question here is that in this scenario, who is the root and then who is the non-root, or maybe who is the root and then what about the designated port and the root port and blocking, etc. Because we are running this spanning tree protocol at the moment. So for that you can go and check show a spanning tree, and then bridge means yourself. So we have two options here. One is the bridge option, that is my, and then what about the root? So I can go and check the bridge address and then the root address, and here you can see that bridge address for VLAN 10, we're focusing on VLAN 10, and root address for VLAN 10, both are same. So that means that this particular switch is the root. Now since this is the root, I want to know that what is the port status. So now if you go here and check, say for example VLAN 10, and say we have option for interfaces as well. Interface wise we can go and check, say E0/0, and then I can check the state as well and detail as well. So interface wise also you can filter. So for example 00 is the designated port. So if you go and refer the topology diagram, we'll find that we have different port from switch that is going to switch 1 to 2, say 00 and 01. And here also you have 0, 0 and 0/1. So this is a DP. That means if you go and check here, this must be RP, correct? Again, whatever we have a study, we are following the same thing. So now if I go and copy this command here, you can see here this is a route forwarding. That's correct. So DP and RP, like that we can go and analyze. Now what we want to know here, I fully want to know the route address and the bridge address. So route address, we know that will be 6500. And now again, if you go and check the bridge address for this particular switch, what is the MAC address? Because priority is the same. Likewise, if you go and check the MAC address for this particular switch, you'll find this is 6700. So as per the lower MAC address, switch 1 is the winner. Now if you go and check this particular interface, that the interface between switch 2 and switch 3, here you will find this blocking. So spanning tree VLAN 10, say for example detail. Now for VLAN 10, you'll find that few of the ports, so this is root, it's okay, 0, 0. You'll find blocking, and you'll find uh, ports here in switch 3. A few of the ports are in blocking stage. Okay, so this is related to STP. All these commands related to STP. So what are the big commands we have, or important commands we have? Show spanning tree summary. It will give you the summary, the spanning tree, and for that particular VLAN, you can check the detail like this. Then you can check, so spanning tree. So for example, sometimes we used to use filters as well. So for example, I can go and check include, and then um, we can filter certain things here. So for example, designated, or then I can add here designated, and say for example other also if I have. So everything is designated forwarding because of this is the route. So here you can see all the ports, they are coming like this. Yeah, so we have option, we can filter, we can add multiple filters as well. Here you can see that we have only 2 port address designated. All right, but what we have to do in this lab, that we have to go and run the RSTP. So I'll go to the switch and we have to change the mode. So spanning tree mode is, and if I type question mark here, you can see that you have mode MST, PVST, and rapid uh, PVST. Now, if you are changing the mode for rapid PVST, you should do this to all the switches, correct? So we'll go here and paste that command to all the switch. Then these switch will get converged. Once these switch will get converged, now we can go and check show a spanning tree, and you have the same options here, correct? So here you can see that for MST you have some other option, but show a spanning tree, and then we can go and check detail. Inside detail you can see that uh, VLAN 1, I don't want to check VLAN 1, but still VLAN 1 is executing RSTP compatible spanning tree protocol. You can check this. Better I can go and run the command show spanning tree VLAN 10 and then detail. So we can check only VLAN 10 commands. Now you will see that the port role will get changed. So DP will be DP. There is no problem on that in switch number 1. But if you go and check this in switch number 2 and 3, as per the rapid STP, the designation will get changed. So this is route, it's okay, designated forwarding, designated forwarding. Now here you can see this alternate blocking. So now you can see that the designations are getting changed. the role of the port is getting changed. So VLAN 10, so a spanning tree, VLAN 10 and detail. Now here also you can see this is the forwarding, alternate blocking, alternate blocking. Alright, so this is the way that we can go and run the RSTP and then we can verify that. Alright, so we can verify like this. Again, if you want to check more options, you can go to show spanning tree VLAN 10. If you want to check root and then other options, here you can see that you have options related to priority, port, hello interval, details, cost, etc, etc. Then if you want to check some other stuffs, here you can see if I go to a spanning tree, again if I want to check the bridge and then the protocol, and if I press enter, so here you can see it is running in RSTP. Same thing that we have in STP, there is no much change, slight change in the configuration, but the verification options are the same for STP as for the RSTP as well.
In 1.2, the last topic we have VPC. This is quite important topic. What I have done that after this particular session, you'll find 4 small sessions. So 4 small 5-minute videos are there that I have recorded in a data center in the lab environment. Small videos, and even you will heard some fan noise as well in the back. Small video just to understand that how you can go and configure the VPC, and in that videos you'll find the small lab topology as well. Great. So we are going to learn, understand the VPC terminologies. What are the steps we have to do the configuration to the VPC in this section? Now, why we need VPC? We know that if we have 3 switches and if you go and connect 3 switches, automatically a spanning tree protocol will come into the picture and it will try blocking. The number is 50% of ports will be blocked. So you don't want uh, to block the ports unnecessarily, because in that case you are not using 100% of bandwidth, because 50% of ports will get blocked. Correct. So to overcome from that particular issue, we can use VPC as a virtual port channel method. And what is happening that when you are using VPC, so in this diagram you'll understand, what is happening that we are clubbing 2 devices and they will work as a one device. So instead having triangle, or instead having multiple link in a network, what you will find that suppose if you have this type of hierarchy where you have your core switch, they will find some straight line to the access switch, and from access switch you have the straight line to the servers. Correct. So in this manner, what is happening that you are utilizing 100% of the bandwidth, because you are not forming triangles in a network. What you are doing, you have the straight line. So if a straight line is there, there is no loop, and that's the use case utility we have with the VPC. VPC is a nice way to provide the data center devices to do use of full bandwidth, all the interfaces inside the data center. Correct. So it will eliminate the STP block port. It can create L2 port channels like LACP, etc. And different type of platforms are there which will go and support VPC. Now in this diagram also you can see that we have block port due to VPC, due to STP, sorry. And then when you are using VPC, that means you are overcoming that problem, and now you have the straight lines. Correct. So since you have these straight lines, so this diagram will look like very simple. This diagram is something like this. So you have a straight lines going from one place to other place. Great. So let's focus, understand more about the VPC technology terminology. Again, here also the same thing, you'll find that while you're doing the migration, whatever block port you have, and this is in the larger, in the broader perspective, and if we have n number of servers, n number of links, So obviously you can increase the efficiency of those at least 50%, because now you are using all the bandwidth, all the links, and even the migration of this non-VPC to VPC, that is also easy to do. Great. So now we understand that why we need VPC, because we want to do full utilization of bandwidth. Now, when we are using new technology, they are coming with new terminologies. Correct. So what are the new terminologies we have? Even I have one small animation slide as well after this, so you'll understand more and more. But the key term here is that you have to define the VPC domain, you have to define the VPC peers, you have to define the member port, and here you can see that everything is marked. You can draw all these things in your notebook, in your copy. Then you have the VPC, then you have the VPC peer link, correct? So you can see this is the VPC. Will in the lab we'll go and define this VPC as a 200. Here in our lab, although we have very small lab scenario, like you have 7K, 7K, and then you have 5K. Here you can go and define VPC 200, etc. But again, you can go down in a hierarchy. So from 7K, you can go to 5K. From 5K, you can go to the fix or the servers, where you can go and create the VPC. Again, the analogy is that you want to create the straight lines. You don't want complexity in a network. So what's the protocol behind the scene? The protocol behind the scene is CFS, Cisco Fabric Services Protocol, that will be used for state synchronization and configuration validation. Because here you are doing some configuration related to VPC, here you are doing some configuration related to VPC, who will be the primary, who will be secondary, who has the highest priority. According to the CFS protocol, it will go and synchronize the database. Let me show you the animated slide that we have. So let's try to understand that how we can go and build the VPC domain or VPC configuration. So first of all, you have to go and define the domain. So domain 10, domain 20, etc. Because different domains having different VPC elements, VPC member ports, VPC member channels, etc. Then you can go and define the peer keep alive. So these VPCs, they have to exchange their control messages. So for that, we have the VPC peer keep alive. Then we have to define about the peer link. So here you have the peer link, and here in the diagram, nice thing here is this, that you can see the colors as well. So when I am talking about VPC domain, you can see the color is light brown. Then green one is your keep alive. You may use management interface, or you may use dedicated L3 interfaces, correct, for the keep alive packages or messages. Then peer link, you can see this third number item is coming as a peer link. Then you can go and create the port channel. So you have the VPC, in our case that will be 200, etc. And then finally you can do rest of the configuration that you will find inside the lab section, correct? So lab section, all the 4 videos, when you watch, you'll find that how we can do a step-by-step configuration, and then how we can do the verification as well. Now coming back to verification, what is happening? First of all, you have to go and enable the VPC feature. So VPC manager will start, then VPC peer keep alive will get kicked off, means the control package message exchange will start. Then peer link will come up, then it will resolve who is the primary, who is the secondary. Then it will go and check the consistency check, means how many VLANs I am supporting, how many VLANs you have, what's the type 1 and type 2, those things in detail, correct? So you should not have a major configuration difference inside the inside both the peers. You should have a primary and secondary role type of configuration changes, that's okay. Okay, and then the peer link will be up for the data. The SVI brought up time, you can see VPC plus 10 second. The VPC's brought up time is SVI is plus 30 second. Great. So once our VPC will be up and running, you can go and use one very small but key command, show VPC. Show VPC will tell you good amount of information, and then you can read those information. If you have at least you will get the high level overview, means you're not getting 100% details, but you can see that 90% of the information it is giving. But again, if you want to do some troubleshooting, deep troubleshooting, then you have to use other commands. But you can see that as per our slide, it will give you 90% of the information, initial situation information, correct? So let's see. Here you can see that CFS communication with the peer, that's okay. Then we hear the keep alive, so it is telling that peer keep alive, we are getting peer is alive, then consistency check is successful, then VPC role. So all important things it is giving you, correct? Peer keep alive, CFS role, the peer information, the VPC role information from one command. And now here in the bottom you can go and read the important description related to all these output that we are getting here, correct? You know the theory. Now let's go and do the VPC configuration. So in this section, we want to do the VPC configuration. And here you can see that we are going to do the dual VPC configuration within the spines and within the leaf as well. So within the spine, we have the port channel in between them, 200 that we have created earlier, but you can see that we have VPC port channel 300, and then within the leaf, we have port channel 100 that also we have created. But from the leaf also to the servers, we have the port channel 55. So what I will do here, that let's just split this into two parts. First of all, I'll go and do the configuration, VPC related configuration here within the spine 1 and spine 2, which having the domain ID of 200, and in the next section, we'll do the configuration for the leaves. All right. So let me pull the server, the lab here, and the resources. Let's do the configuration. Right. So how we can do, first of all, the first step you should do is to enable the feature VPC, right? Now, once you enable the feature VPC, then you can go and do the rest of the configuration. So let's do that. Let's go and define the domain. So we have VPC domain 200. And then now we are within the VPC, where we will go and give the configuration, because everything I have covered in the theory. So let's make this be a switch, and then the role priority. So I'll go and give the role priority of 1000, and the spine 2, I'll go and give the role priority as 2000. Then we should go and define the keep alive. So keep alive, my destination is 4.202. That on the other side, it should be given. I will go and check the management IP. This is the management IP, the VRF management that we can verify. Let me go and quickly check that. Show IP interface. Brief show run interface management. Oops. 0. So you can see that is the management IP, right? So we are doing good. Then let's go and give this as a peer gateway as well. So all security parameters we are giving: peer gateway, peer switch, auto recovery, and then finally the sync for the ARP. So once we do this much, this is the VPC configuration, then I should go to the port channel, right? So we have the port channel. Let's go and check. Show port channel summary first of all. And we have port channel 200. Now we have port channel 200, that this port channel is our peer link. So I can go to interface port channel 200, because this is our VPC peer link that I should do. But we have a downlink as well. So what are the interfaces that we have as a downlink? So we have interface E1/3 and 4, right? Where we want to configure channel group 300, mode is active, right? This is going to the leaf. And once we have this configuration, then let's go check the E1/3 as well. Make sure that we have the allowed trunk and all right. Now I can go to this port channel 300. Make sure that switch port mode trunk, switch port trunk allowed VLAN, switch port trunk allowed VLAN 10 and 20, and then very important command, that is VPC 300, right? Great. Let's go to spine number 2 and do the same sort of configuration. So spine number 2 also will go and enable the feature VPC. Once we have this feature, we can go and create the VPC domain 200. Then I can go and do peer switch and peer gateway. Then the role priority here will give 2000. And then we should go and give the peer keep alive destination. Just it should be a reverse. So 184.201 is my destination because myself is 198.184.202. Then I can go and do auto recovery, and final is IPRP synchronization. Now in this switch also we have interfaces. First of all, the peer link. So I can go to the port channel that is 200 where I want to enable this VPC peer link because both sides we should enable this. And then I can go to interface E1/3 and 4, right? Where we should go and do the configuration related to channel group 300 mode active, because over this interface port channel 300, we want to make VPC 300. All right, this much configuration. You can pause the recording and note it down the configuration as well. Now we can go and check the show VPC. So now you can see that show VPC peer is okay, is alive, success, it is enable, port channel 200 is up, the VPC 300 is status is down. That's okay. We should have configuration from the leaf side as well. But this is the way you can go and do the configuration from the spine side, and then we can go and do the configuration from the leaf side as well. So let's just stop here, and the next section will do the configuration from the leaf side. All right, let's do the configuration to the leaf side. So the leaf side will go and do the configuration, and you can refer the diagram that we have earlier, that from the leaf side, we have interfaces 5 and 6 that is going towards the spine. And from the leaf side, we have interfaces that is going towards the server as well. That is, we will go and verify that the interface is 1/3 in one side and 1/4 in the leaf 2. Like that, you'll understand once we'll do the configuration, and please refer the topology as well. If I have the topology, let me first of all log in here. Let me quickly show you the topology and then we'll do the configuration. So we have the topology here. You can see that interfaces 5 and 6 where we have to create this port channel 300, and then you can see that we have port channel 100 as well. This port channel 100 will go and make as a peer link, VPC peer link, right? So we have back-to-back VPC, dual VPC, and then we have interfaces. On leaf 2, we have interface 1/4, and leaf 1, we have interface 1/3, which is forming the port channel 55 with VPC 55. So like that, we have to go and do the configuration. Most of the configuration will be same only. So if you go and check VPC, that's a configuration. So here we have the domain called 200. There we'll go and take domain as 100. We need this command. We need this command, right? So I can even go and copy and paste here what is the source and what is the destination. we'll go and verify. There we have 102 instead of 202. Let's do that. Let's go and do the configuration. Let's go and enable the feature VPC domain 100. Once we are under the domain, then I can go and show the command. Just copy pasted the command that peer keep alive is 102. Source will be 198.184.101. So likewise, we have the configuration items that we can copy and paste. So these commands also I can go copy and paste. Then we should go and create we should go to interface port channel. What's the port channel we have where we want to do the keep alive? So that is 100, where we have to do this VPC peer link, right? Keep alive and all those things are already there. All right. Show run VPC. You can see the configuration. So we have enabled the feature, then we are going there, and then in the other side of the configuration, our priority is 2000, right? You can check here the VPC configuration, and it's a little bit slow. And then rest of the configuration, I can go and use the keep alive in the reverse order. So this will be 101 and source will be 102, right? Then rest of the line items also can copy paste because it is almost the same. So likewise, we can go and do the VPC configuration. But apart from that, we have to go and create the dual side VPC, right? Dual side VPC means that we have interfaces. We have interfaces E1/5 and 6, right? 5 and 6, these are the interfaces where we want to create the channel group 300 mode active, because once we have this port channel 300, we can go to this port channel and we can make this VPC 300, right? So this configuration also we need. So I can go ahead to leaf 2 as well. Interface E1/5 to 6, right? And we have to create this channel group mode active, and then we can go to interface port channel 300, where again we can go and make VPC 300. Now this is the configuration. Now if I go back to spine number 1 and we do show VPC earlier, you can see that it was down, right? Now you can see that port channel 300 is up. Now the back-to-back VPC is fully configured with respect to spine 1 and spine 2. Spine 1 and spine 2, earlier it was down, now it is up, success. But with respect to leaf, again leaf they are connected. So one leg is going to one of the server. So leaf 1, I can go to the interface E1/3, where it is going towards the server. So here I can go and create the channel group 55 mode active. But on leaf 2, right? On leaf 2, this is interface E1/4 as per our diagram. So here I should go to channel group, channel group 55 mode active. And now I think we are done. So now here also we can go and check the show VPC. It will show you the back-to-back connectivity, success, up, right? And here I can go and check show VPC. And this is showing up. So we have done all those configuration, and we should go to the last piece, interface port channel 55, because we have created the port channel here. Show an interface port channel. Let me check that configuration first. Okay. port channel 55, switch port mode trunk allowed VLAN, and should be a spanning tree port type edge trunk because it is connected with server, and should be VPC 55. Likewise, I should go here to the interface port channel 55. You know that those commands will be there: switch port mode trunk, switch port trunk allowed VLAN. Here the allowed VLAN on this interface, let me show you this before doing anything. Show an interface port channel 55 E1/4, you can say 10. And then over this interface, I should do the spanning tree port type edge trunk, right? And finally, VPC 55. And now we have the full-fledged configuration for entire VPC. Now you can see that it is up. This is back to back with the spine, and this is to the server. So we have the dual VPC scenario fully covered, fully configured. All right, let's just stop here. Hi everyone, thanks for listening this message. In recent times, we got messages that do we have any program, any course where we can go enroll and we will be very much eligible for the job market. What does it mean? That if you go and check the IT portals, you can see that you have different course packages for CCNA, then CCNP, then firewall, then cloud, then automation, etc. Right? So what we have done that we created one program for those engineers who want everything at one place and they are new to the market, or maybe they want to enhance their skill set. So we created such program, Joint. Joint is something like job-oriented internetworking training. Now in this program, you can see that we have added CCNA routing switching, cloud virtualization part of VMware, CCNA or associate level wireless knowledge, Cisco Meraki, Google Cloud associate level knowledge, not entire course, but how much you need to get clear in your interview, or when you are working on this cloud environment, you are not new to that cloud environment. Then Python, then routing switching, ASA firewall, and then we are adding firepower as well. So not only ASA firewall, but next generation firewall. Then we are going to add Cisco SD-WAN, Cisco DNA, etc. Like what we want, that we want to make this course as a complete package course in terms that once you go and complete these areas, you can write in your profile, in your CV, that you know these technologies. And apart from that, not only this course, once you go and use the Joint 9, that's the code here, and if you apply, you will get maximum 85-86% discount on this course. So not only that we are offering the discount coupon, but apart from that, we are giving the lab, EVNG lab. So whoever will go and join this particular course, they will go and get the EVNG lab as well, so they can practice routing switching, right? So what you need a solid foundation, solid course where you can gain the technology knowledge. Then you need the lab environment where you can go and do hands-on practice. And then you can go and add these areas in your profile and go for interviews and all, right? So on other words, in simple words, I can tell this thing that if you go to Udemy or YouTube, I have so many different courses I created just to obviously earn money. So many courses I have, but this is the only course I created actually for the IT professionals, actually for you, where I want that you can go and get the job. That's why I have added whatever I have 15, 16 years of training experience. I have added all the best things from there in terms of that you gain knowledge whatever gray areas you have. Someone knows networking, don't know automation and cloud. Someone knows networking, they don't know firewalling technology, security areas. So that means that you can go enroll this course, gain the knowledge on those areas that you don't know. Or suppose if you have only 1 or 2 years of experience, then you can start this journey, complete the entire course within 5 to 6 months or maybe 3 months, and then add these things within your CV profile and get the job. So this is something like job oriented or career oriented training that is going to help you to get the job and right knowledge to showcase in your profile. All right. Thanks for watching this video.